Let's look at a bit about the simplest random variable, the constant random variable. It's just a simple example. So let's do an example. Assume that x omega is some constant for all omega. So then what can we say? What is the distribution of x then? Let's look. We need to look at the pre-images. So px of b is now the probability of the pre-image by x of the set B. Yep. And now assume that C is some real number. So C is here. This is the real line, and this is the omega. So what can we say about the pre-images? So if B contains C, then this is the full set. Yep. So this is the probability of the full space if B contains, and that's 1 if B contains C, and it's the probability of the empty set, which is 0 else. So actually we can conclude that the probability that, let's also recall that this is the same, that the probability that X belongs to B. So we conclude that probability X belongs to B is 0 if, well, C is not in B. It's 1 if C is in B. Well, it's very trivial, but this trivial thing has a name. It's called the indicator function of B. And we could write it this way. So that's what's called the indicator function of B. And in the lecture note, maybe it's there's a different name for it, so or symbol. So I think Kalle might be using this type of notation for the indicator function of a set. For me, this is too difficult to write, so I might just use this symbol which I'm used to. Okay. So we know that probability X belongs to B for a constant random variable. It's an indicator. It's 1 or 0 according to C is in B or not. So we could write it as an indicator B of C. But what's wrong with this indicator notation? Look at this. This indicator is a function which maps C into indicator B, C. So it's a 0-1 map, but it's mapping C to something. On the other hand, we were now thinking that our random variable is C, where C is a constant, which is fixed. So we don't want to look at things as a function of C. We want the kind of dual point of view. We want to look at things where we map actually B. So what about we want actually to study that we map set B, which is mapped to 0 or 1. So in the sense we would like to have a set which is mapped in this way, where set is mapped into a number and not a number mapped to a number as it would be there. So in that case, we actually use a different notation. We write this using a different notation. We say that it's some function of C evaluated at B this way. And this is the Greek symbol delta. And delta can be defined in this way. And now, if you look at, we define delta C of B again. We define it in the same way. It's 1 if C is in B and 0 else. So now this is a well-defined map mapping a set to a number. And this is called, delta C is called the Dirac measure at C. And an exercise for you if you want to check that delta C is really a probability measure. On the real line. So every Dirac measure, you can fix a point, and then it means that you could also think that it's a kind of unit mass at C. So you can fix a point on the real line and you kind of place a unit mass at that point. So that's what you call a Dirac measure. And what we learned here is that if we have a constant random variable, so that whatever the little omega, you always map it to a constant. So with this calculation, we know that the law of X, this probability measure here, is actually equal to, this is equal to the Dirac measure at C of B. Our conclusion is the law of a constant random variable X omega identically C is, we could write it this way, it's equal to the Dirac measure at C. All right. Something very trivial, but introducing some new notations and new ways of thinking from the dual point of view that we map sets into numbers, not numbers into numbers.